Hi everyone, welcome to this video on boundary element method or BEM. In this lesson, we'll explore the main differences between BEM and the find element method or FEM. If you already know FEM, this video will help you see when and why BEM can be sometimes a better choice, especially for certain types of engineering problems. Let's get started. To understand the boundary element method, let's start with a simple one-dimensional example, a prismatic rod. The rod has length L and a constant cross-sectional area of A. At the left, it's fixed at x equal to 0, and at the right, it's free at x equal to L. The governing differential equation, shown here, represents equilibrium in terms of the displacement u. It is written in the strong form, where we directly relate the applied load Fx to the internal stress term involving Ax and the displacement gradient du over dx. Here u is the primary variable representing the displacement, and the term q, which is A times du over dx, is the secondary variable, which represents the internal force or stress. This simple setup will help us clearly see how the boundary element method works compared to the find element method. In this one-dimensional example, the domain is simply a line that extends from x equal to 0 to x equal to L. The two boundaries of the domain are just the two end points, because the domain is 1D. We have two variables, the primary variable, which is displacement, and the secondary variable, which is Q, that shows stress or force. At each boundary, one of these variables can be prescribed depending on the boundary condition. At the left end, the rod is fixed, so displacement is known and it is equal to 0. That is essential boundary condition or EBC. At the right end, there is no external force. So this means that QL is equal to 0 at the right end. That is natural boundary condition or NBC. So this 1D problem is completely defined just by the two boundary nodes. A key reason why the boundary element method focuses only on the boundaries rather than the entire domain. To derive the boundary element formulation, we start from the strong form of the governing differential equation. In step 1, we multiply the equation by a weight function called Wx and integrate it over the entire domain from 0 to L, as you can see here. This gives a general domain integral form of the problem. In step 2, we apply integration by parts or IBP. This step transfers the derivative from the displacement u to the weight function w and introduces boundary terms at x equal to 0 and x equal to L. If you would like a detailed explanation of how integration by part works in this context, you can refer to the first video about IBP in my BEM playlist. After applying the natural boundary conditions, the resulting expression is called the weak formulation. For a deeper discussion on the weak form, you can also watch the first video about the weak form in my FEM playlist. So this slide marks the transition from the strong form to weak form. The same foundation used in FEM, but we'll go one step further for BEM. To move closer to the boundary element formulation, we perform integration by parts one more time to derive the inverse formulation. So for second integration by parts or IBP2, we start from the weak form, and when you do integrating by parts, we shift all of the derivatives and transform the remaining domain integral into boundary-only terms, as you can see here. Now the equation depends solely on the value of u and q at the boundaries, specifically at x equal to 0 and x equal to L. We have all of the boundaries, EBCs and MBCs now in the inverse formulation. So we have u0, ul, q0 and ql. All of them are now shown in the inverse formulation after integrating by parts for the second time. This is the essential idea of the boundary element method. Instead of solving throughout the domain as FEM does, BEM expresses the entire problem in terms of boundary variables only, making it specifically powerful for problems with infinite or semi-infinite domains. So what really happens when we move from the strong form to the weak formulation? First, the natural boundary conditions automatically appear in the equation. That is why we see the secondary variables Q0 and QL showing up at the boundaries. This is an important feature because it connects the mathematical formulation directly to the physical boundary conditions of the problem. Second, the order of derivative is reduced. In the strong form, we had the second derivative of u or d over dx of du over dx, but in the weak form, only the first derivative or du over dx remains. That is why it's called weak. The differentiation has been weakened. This step is what allows us to use simpler shape functions and obtain smoother solutions in finite element method. And as I mentioned before, if you would like a more detailed explanation of the weak form, check out the first video about weak formulation in my FEM playlist. Now let's see what happens in the inverse formulation, the result of applying integration by parts twice. At this stage, all boundary conditions appear in the equation, both the essential boundary conditions, which involve displacement u, like u0 and ul, and natural boundary conditions, which involve force q, like q0 and ql. So we now have u0, ul, q0, and ql all showing up explicitly in the inverse formulation. You can also see that the entire differentiation has been now transferred to the weight function. So we have d over dx of a times dw over dx. That means that the displacement variable, or u, no longer carries any derivative, or we can say it's fully integrated out. In other words, performing double integration by parts extracts all EBC and NBC terms and gives us the key foundation for boundary element method. We have reduced the entire problem to terms that exist only on the boundaries. Let's now compare the finite element method and the boundary element method. We'll start with FEM, which is a domain-based solution. In FEM, after performing one integration by parts, we obtain the weak form, but this weak form still contains domain integrals. That means both the weight function w and the primary variable u are defined throughout the entire domain, which is 0 to L in 1D problems. The domain is shown with omega and the boundary is shown with gamma. Because of that, the domain has to be discretized into elements, and only after assembling those elements do we apply the boundary conditions. So the finite element method fundamentally depends on what's happening inside the domain, not just along the boundaries. That's why we say FEM is a domain-based solution, and it requires evaluating the field quantities everywhere inside the region omega, as you can see in this integral here. Now let's look at the boundary element method, or BEM, which is a boundary-based solution. In BEM, we start with the inverse formulation, the equation we obtained after performing integration by parts twice. The key step here is in how we choose the weight function wx. In BEM, this function is selected as the fundamental solution, also known as Green's function, which already satisfies the governing differential equation inside the domain. Because this fundamental solution captures the domain behavior analytically, all the domain integrals can be transformed into boundary integrals using Green's identities. This means that the entire problem can now be expressed only in terms of boundary quantities, the value of u and q at the boundaries, as you can see here, u0, ul, q0, and ql. So unlike FEM, there is no need to discretize the interior. That is why we say BEM is a boundary-based solution. It works entirely on the boundaries, while still representing the behavior inside the domain. Let's summarize the key difference between FEM and BEM. In the find element method, we stop after performing one integration by parts, so our unknowns exist inside the domain. That means we need to discretize the entire volume, the whole region where the problem is defined. In contrast, the boundary element method performs integration by parts twice, and it introduces a fundamental solution, or Green's function, which analytically satisfies the equation inside the domain. As a result, we only need to discretize the boundary, not the interior. So in simple terms, FEM performs one integration and it meshes the domain. But for BEM, we have double integration. And using the fundamental solution, we only need to mesh the boundary. That is the essential difference between these two powerful numerical methods. I have summarized the differences between FEM and BEM in this slide. So considering the formulation domain, FEM is based on the domain formulation or weak form, but BEM is based on boundary formulation or inverse form. So in FEM, the governing equation is integrated over the entire domain omega, but in BEM, governing equation is integrated twice and only on the boundary values. Considering the discretization, we discretize the whole domain in find element, but in boundary element, we only discretize the boundary. Considering the unknowns, in find element, field variables like displacements are the unknowns inside the domain. But in boundary element, field variables only on the boundary are unknowns. Interior values will be computed later. Considering the integration type, we have just single integration by parts to reach weak form in find element, but in boundary element we have double integration by parts to reach the inverse form. Considering the computational cost, FEM requires large systems, many elements, especially in 3 dimensions, and we have sparse stiffness matrices for FEM. But for BEM, we need to have a smaller system because we are just working on the boundary. And considering the applications, we can say that FEM is ideal for nonlinear, heterogeneous, and large domain problems, but boundary element is ideal for linear, homogeneous, infinite, or semi-infinite problems, like the problem that we have in soil mechanics. This figure summarizes everything we've discussed. On the left, for FEM, we perform one integration by parts, and the solution depends on what happens inside the domain. That's why we need a domain mesh, as shown here. On the right, for BEM, we perform 2 integration by parts and use a fundamental solution that already satisfies the behavior inside the domain. As a result, only the boundary represented by this outer curve needs to be discretized. By discretizing boundary, I mean something like this. So we discretize the boundary into various or a number of boundary elements. So FEM works within the domain while BEM works only along the boundary. That is the core conceptual difference between the two methods.